This is your floor. Go ahead, Brad.
Thank you, Yang, and thanks for everyone for letting me say a few words about my very recent research. So what I would like to talk about today is an old topic, and that has to do with the so-called coherent potential approximation, which we can be easily combined with DMFT as the simplest theory for disorder and interactions. However, we recently discovered that this theory is actually better than we all thought, and it could be of more direct relevance to experiments, which I think could be of some interest to this collaboration as well. So this is work done by mostly by my current student, Yu-Ting Tan, and some of the results are unpublished. Some of it is already on the archive. Oops. Okay, so concerning literature, I mean, that could be of relevance. There is this old book we edited some years ago, about 10 years ago, that has some overview of metal-insulator transitions for those who are not familiar, as well as some of the DMFT approaches to the same problem. But to those who like an introduction to how to treat disorder with Green's functions in the context of tight binding models, my favorite book is the Economo book, which is very pedagogical for students and for everyone to really learn how all this works, what is CPA and some of the history. It's a beautifully written book by Springer. And also there's a very recent preprint on the topic with my student Yu-Ting Tan, and which has just been posted on the archive very recently. So in general, we know that metal-insulator transitions, in absence of symmetry breaking, can have two different driving forces. One is the interactions that Mott talked about, and the other one is disorder. The interactions are particularly important for narrow and high-field bands, and there are many materials in this regime. There has been much talk about this in recent years, as well as within this collaboration. But it's restricted, the Mott mechanism is restricted to some special cases. There are a lot of other materials which are not exactly in that regime, and perhaps the mechanism of Mott is not of direct relevance, but the disorder could be playing a very important role, and that's what I would like to focus on today, on the effects of disorder that Anderson emphasized in his pioneering work. Of course, before I go into details, let me just say that this problem of metal-insulator transitions has been a difficult problem to tackle for some very general reasons. The reason is that it is a form of sharp phase transition, in this case at zero temperature and involving quantum mechanics, but it's a phase transition similar in many ways to other second-order phase transitions, which we have learned about in our courses and in the history of physics. It goes back, there are many ideas go back to first to Landau, who introduced an idea of spontaneous symmetry breaking and introduced Landau-Ginsburg theory. And later on, this has been a springboard for much more sophisticated treatments where corrections to mean field theory were systematically included. And this led to an approach based on expanding around high dimensions, because these mean field theories or the Landau theory is exact, making the exact in high dimensions. And then as you go below some upper critical dimension, you can compute the systematic corrections. And this program has been extremely successful for most critical phenomena. However, in our case, in the metal-insulator transition, especially when disorder is present, a strong disorder is present, then the two phases, the metal and the insulator, do not differ really by any static symmetry. And this powerful bag of tricks that Landau and his followers introduced is really not very helpful. We don't even know what is the proper Landau theory or what is the upper critical dimension. Is there one? And that's a very difficult open problem. For this reason, in the late 70s and especially in the 80s, people tried to approach the problem from the opposite point of view, from the lower critical dimension, because they found that disorder effects are stronger in 1 and 2 dimensions, and it's been suggested that in 1 and 2 dimensions you don't even have, strictly speaking, a metallic phase. So this method was based on expanding around 2 dimensions where the transition finds itself in the regime of weak disorder. So these are perturbative treatments confined to weak disorder. However, this type of theory, which has been developed in a very beautiful formal approach based on the so-called nonlinear sigma model by Finkelstein, has been extremely popular, but also extremely useless, because essentially no experiment on the metal-insulator resistors have ever been analyzed successfully and explained by these theories. And the reason is presumably because the real transitions do not happen at weak disorder, nor are there in absence of interactions, and so this kind of approach is perhaps quite misleading. So people would like to try some other ideas, and there's been quite a bit of activity in recent years, going back to some sort of order parameter theory or Landau theory. So before I go into details, let me just mention that the problem of disorder in non-interacting system, the so-called Anderson localization, has been studied quite a bit. But in very recent work, we have in fact developed a strong disorder approach, which is complementary to this weak coupling 2 plus epsilon method. And this approach, based on some sort of real space RG, which is very accurate at very strong disorder, has been, turns out, very successful and very accurate. You can reproduce all known results and in fact compute exponents in all dimensions from 2 to 3 to infinity. And what this theory showed is that there is actually no upper critical dimension. The Anderson localization is a rather bizarre and unusual type of transition, but it also shows that it seems that the behavior is could be well understood by expanding not around low dimensions, but around high dimensions. It turns out that expanding around low dimensions in several different ways gives very diverging and misleading results. And it suggests that the right approach is in fact going to high dimensions. So keeping this in mind, we would like to develop a theory with disorder, with interactions, which is controlled in high dimensions, and then introduce corrections. So the theory that we're all familiar with, it becomes exact in the limit of large number of neighbors for large coordination or large dimension, is dynamical mean field theory, and it can be augmented to introduce disorder. The idea is that when you have many neighbors, you can replace the environment of a given site by some average or typical medium, and then uniform medium with a modified band structure, which is self-consistently determined. We all know how this works for strong correlations without disorder, but it can be also, it turns out that if you put disorder in all kinds of models, that in this limit, the so-called coherent potential approximation becomes exact, and it replaces complicated spectra of electronic states by some sort of average spectrum, which is self-consistently determined. Unfortunately, this method, at least in the non-interacting limit, is not able to capture the metal-insulator transition because, as it turns out, at least when you have a standard flat distribution or some featureless distribution of disorder, then you find that this kind of disorder in the limit of high dimensions within the coherent potential approximation just broadens the bands and nothing much happens to the density of states. So if you focus on that theory alone, you'll not find any disorder-driven transition in the non-interacting limit. And that's been basis of most people putting down CPA as a useless and not interesting tool, except as far as the metal-insulator transition is concerned. Here are some results that Tanya obtained in one of the recent articles, showing how the density of states evolves as you increase disorder in a single site CPA approximation, but also when you add cluster corrections. And it turns out, as we can see, the band given by this dashed line, this is the average density of states, just broadens, nothing much happens. The red line shows these so-called typical density of states, which is sensitive to localization. So we can see that there is a Anderson transition, but CPA doesn't know anything about it. So at first sight, it suggests CPA is really a pretty bad theory. And that's why I guess most people, or some people at least, who are interested in the transition have a very low opinion of that. However, there is something really missing from this theory, which we can understand if we take a look at several recent experiments using scanning tunneling microscopy, which can directly look in real space at the system using scanning tip, and we can measure the density of states. So this is here shown the density of states for various systems with strong disorder. Here you can see that system is very homogeneous. There are several such systems probed. And every time, as we approach the transition shown here, you see that there is a gap opening at the transition. Now, this phenomenon of gap opening is something that totally doesn't happen for Anderson localization alone in the non-interacting limit. And it signals the fact that the interactions play some sort of role, which is very important, and perhaps completely modify the nature of the transition. So, this result, this very important results, which hasn't been really appreciated in the past, is in fact goes hand in hand in what Phil Anderson said in his Nobel Prize winning lecture, where he was afraid that the interactions could be doing something unpredictable, but he says that the Mott and the Anderson effects supplement, not destroy each other. What he meant by Mott is some effects of interactions. As we will see, for strongly disordered systems, this is in fact the case, that the interactions in many cases help disorder localize further. And in fact, this interaction, in fact, can be dominant. Although I gave another lecture for this collaboration discussing Mott systems with weak disorder in which the behavior is opposite. And I said at the time that I was very proud to prove that Phil Anderson was wrong at least once. But I think concerning strongly disordered systems, I think that he was right. And in fact, most of the ideas that we need go back to him. And in particular, a few years after discovering Anderson localization, Anderson had another brilliant paper, the Nature paper in 1972, which is known by very few people. And he discussed bound states in amorphous systems, in strongly disordered systems. And he said that if you turn on the interactions, in this particular case, he was talking about the electron-phonon interaction, that what these interactions do, if you have such, so you have several bound states which are occupied by electrons, then if you turn on the lattice deformation, then what will happen is that the lattice will deform to make the potential wells confining the electrons even deeper. And so the energy level, the energies of these occupied states will be suddenly lowered, opening some sort of gap between the occupied and empty states. So this is a simple mechanism that can open gaps in disordered systems. This has been seen in some strongly disordered insulators, and he discussed that in this early paper, but he didn't tell us how we go from a metal to this regime. This mechanism is a polaronic mechanism, and similar polaronic mechanisms were discussed, in fact, also by Lev Gorkov in recent years in the context of transition of metal dichalcogenides. These are lattice polarons, but in fact, very similar mechanisms are found if you consider a coupling of electrons to magnetic degrees of freedom, magnetic polarons, or even electronic polarons, where disorder and the long-range Coulomb interaction can also help self-trap the electron further and stronger than in the non-interacting limit, opening some sort of gap at the Fermi surface. So there seems to be a very generic effect of interactions, which really corresponds to the fact that if you have a non-uniform electron density, then in regions which are electron-rich, those regions will be more affected by interactions, helping the electron localize further. And this is something that perhaps could give an answer why is the gap opening at the transition, and how should we modify the theory keeping this in mind. So the simplest theory describing this effect is what I'll show you some results at the end, but it's the theory that we developed with some Italian collaborators several years ago, Simone Frattini, Sergio Ciucchi, and Domenico De Santi. And this is CPA-DMFT theory. In fact, in those papers, we in fact even used typical medium theory, but the simplest theory that captures this effect is CPA coupled with DMFT. And the model is not the Hubbard model, but it's a model describing physics further away from the Mott regime, where we think that something like electron-phonon interaction or maybe the long-range Coulomb interactions play a role, which can be described by a coupling of an electron to some collective field, some bosonic field. In this case, we use the simplest Holstein model with a dispersionless boson, but the principle is more general. So considering this kind of model in the limit of high coordination gives us a self-consistent set of equations, which I won't describe here. But what I want to emphasize, though, here is the most important result. When we have interactions, then normally the interactions introduce a self-energy to the system, and in a non-uniform system, the self-energy in this high-dimensional limit is local, but it can be space-dependent or position-dependent. And so it renormalizes the site, at the lowest order, it renormalizes the site energy. So the disorder distribution is renormalized. And let me show you how it's renormalized. Here we are increasing the disorder. You can see the distribution of renormalized disorder is broadening, but it's also becoming bimodal, and before the transition is reached, it becomes gapped. So this is the mechanism that completely changes the form of disorder. And once this happens, then something magical happens to CPA. CPA, as it turns out, for my bimodal distributions like this in general, will describe splitting the band into two bands and a metal-insulator transition. What's remarkable is that this phenomenon is very, very robust, as we described by this theory we discovered a few years ago, and it applies not only at half filling like the Mott effect, but in fact at arbitrary filling. Whenever we have disorder, strong disorder, and moderate interactions, then the combination of the two will lead to opening of a gap at the Fermi surface, simply to lower the occupied states. And this robust mechanism now completely changes the picture and allows CPA in its simplest form to describe a disorder-driven transition. So what I would like to do in the rest of the talk, what I would like to really focus on is not the details about this particular application that we put in the recent preprint, and that's relevant for some more materials where it works extremely well. But I would like to explain what happens within CPA when we have such bimodal distribution. I will give some simple examples, but the principle is very general. And it turns out that whenever we have a binary type of bimodal disorder, the situation is completely changed. So I would like to show you some results here, also obtained by Hannah in her recent work. And this result has been obtained by treating the average density of states using CPA and its cluster generalizations, DCA, CPA, and also by typical medium theory, which can also describe localization. And I would like to show you some remarkable features of how the result is modified now that the disorder it has a bimodal form. The equation for CPA is extremely simple. This is an equation for the average Green's function of the average density of states. It looks something like this. It's a nonlinear equation, but when we introduce a bimodal disorder, then look what happens. Here we are increasing the splitting between the two site energies, and at some point the two bands split. So what's really remarkable, you see that in contrast to the uniform disorder case, here the opening of this gap affects, as you can see here, the states near the Fermi energy much more than elsewhere. Red are the extended states, white are the localized states. So you can see that many states in the bands remain extended. So you're not very close to the point where the entire band localizes. So disorder is not yet very, very strong. Oops, I'm losing my earbud. But when the gap opens in the average density of states, this immediately also leads to Anderson localization. And so what we can learn from this is that the opening of the gap in the average density of states can be considered as the driving force for this transition. What's also remarkable is that there is a particular prediction for the transition obtained just by CPA. Here we can see the gap opening. And if we go to cluster corrections, this result is really not modified very much. So in the case of binary disorder, what's really very surprising is that the prediction of the simplest CPA theory is a reasonable starting point for the transition, as opposed to a situation where a flat distribution of disorder where CPA was simply terrible and strong disorder. So it seems that, in fact, whenever the gap in the average density of states can open, then this is really the dominant effect, and we perhaps need a much simpler theory than we would be led to think by focusing on flat distributions of disorder. What I would like to reemphasize once more, the argument and the results that I've just shown you on the previous slide show that, in fact, the bimodal distribution of disorder, which is qualitatively the same as binary, is in fact looks like it's a generic form of disorder for interacting systems, but not for non-interacting systems. So this is something very encouraging that, in fact, perhaps the answer to this puzzle is simpler than one would have guessed. And now let me analyze this transition in great detail. This fact that binary disorder can split a band has been known for, I believe, more than 50 years. If you open even the Economou book or similar books, it's been discussed, especially in the context of binary alloys. So this is not really a new discovery. What I discovered just by trying to solve this equation more carefully is that there's a transition that happens that has all features of the second order phase transition. It shows beautiful critical behavior, scaling, and all features of quantum criticality. And I tried to quiz many people who are experts in this. And I could, apparently the details of what this transition looks like exactly, how to solve it precisely, and what are the critical exponents and so forth. To the best of my knowledge, this has not been discussed in the literature for reasons that I'm not completely certain. At any rate, here are some results that I'm proud to say that after 20 years, I actually wrote some code recently. And these are plots that I made myself, numerically solving the CPA equation for a simple model of binary disorder. Of course, I've looked at other bimodal distributions, but you get qualitatively the same behavior. And as it turns out, the critical behavior of the critical exponents are identical. So you can see here, we're starting with a single band. Then we introduce binary disorder. And once this splitting between the two site energies is large enough, then the band splits. You can see here the density of states vanishes, and now the gap is open here, over here. So this is a very, very well-defined metal-insulator transition. As it turns out, the conductivity at zero temperature also drops and vanishes in a linear fashion at this transition, independent of the details of the band structure, of the form of disorder, or anything else, other than the fact that it needs to be bimodal. So let's look in some detail at how this happens. So here is the seemingly simple equation that describes this. If you make this distribution P of epsilon to be bimodal, like two delta functions or two pieces which are disconnected, then you get the transition. But let me consider the simplest example where we have simply two delta functions and a bimodal distribution. Then this equation is basically the sum of two terms, and X is the concentration of one or the other component in this binary alloy. So this is as you can see, a cubic equation. It's a very simple equation. And so what I can do first is I can sit at the center of the band where the gap first opens at zero frequency and look at the density of states, which is proportional to the imaginary part of the Green's function, and look at what happens. So here's the equation for this density of states delta. It's a nonlinear equation, but if I expand it in the powers of the density of states, why expand? Because it is going to zero, so it is very small on the metallic side, but close to the transition. Then I find that it vanishes with the exponent 1/2, just like in a Landau theory for a magnet, for a ferromagnet. So this is remarkable, and in fact, what I should stress here is that this strategy is not new. This is a strategy that Landau developed. He suggested that if the order parameter is decreasing smoothly towards the transition, then we can expand in the powers of this order parameter, and within certain mean field theories, then the self-consistent equations reduce to a polynomial in this order parameter, and then the values of the exponents are strongly constrained and generically assume very simple values, which are either fractions or integers. In this case, similarly to the Ising model, we get exponent 1/2 for the density of states. And if we sit at the transition and look at the frequency dependence of the order parameter, it vanishes as we approach the Fermi energy with the power 1/3, which is also the power that the magnetic field exponent for the magnetic field exponent within Landau theory. So it turns out that for the very same reasons that the Landau theory has simple exponents, here the self-consistency condition is takes the form of has an analytic Taylor expansion in the powers of the density of states or the parameter, and you can find the similar exponents. I would like to mention that this example that I've shown is specific to a half-field case with binary disorder, which is 50-50. But of course, I studied very carefully what happens also if we have other fractions, other fractional weights for the two components. If then the transition is not at the center of the band but somewhere else, and you don't have particle Hall symmetry, nevertheless, for the same reasons and in general Landau theory, it turns out that the self-consistency condition is always assumes an analytic expansion in the powers of the density of states. And whenever that is true, then, as Landau first taught us, then we find universal exponents. We always find exponents which are independent of the details of the macroscopical model, of the parameters describing the lattice, etc. So at least in the limit of high dimensions within this mean field theory, this is something very, very similar to the critical point. I don't show this here, but in fact, you can take this family of curves here that I showed here, and close to the transition, you can show easily that it displays scaling. So the family of curves can be collapsed on a universal scaling function. And this can be shown even analytically within the context of this kind of expansion, within this kind of Landau type of theory, following step by step the prescriptions and the lessons we learned from Landau. So this is a very well-defined critical point with universal exponents. And I've been particularly thrilled to see that if you remove particle Hall symmetry, if we take an arbitrary form of disorder, arbitrary form of the density of states, and none of these features change. And the reason is exactly the one that Landau told us, the fact that a self-consistency condition has an analytic expansion in the powers of the other parameter, that's sufficient to give you universality of the exponents. Now, I would like to also show some features of this transition, which is something that I'm even more excited about, and that's the following. You see, if you take CPA, you start with a band, it splits into two bands. So you may think, well, you know, this is very similar to the so-called band crossing transition. If I start with any model that has a periodic lattice with two sites per unit cell, say you have two sites with two site energies, but they're periodic. Then you will find two bands like this. So this is numerical results obtained for a particular model with two site energies per unit cell. And you get two bands, according to Bloch's theorem. These two bands are completely independent because if you go to momentum space and diagonalize the Hamiltonian, you find that the Hamiltonian becomes Bloch diagonal. So the two bands are completely independent. The band index is a good quantum number. And no matter whether the bands overlap or they don't, you always have two bands, and each band has two band edges, which are branch cuts. So each part of the spectrum is a branch cut, and these two edges are branch points at the end of these branch cuts. So when the bands are split, we have 4 branch points. When the bands are overlapping, we still have 4 branch points. So there is no qualitative change. If you follow each band across this band split transition, it evolves smoothly and analytically. Nothing happens to the band. Each band doesn't even know whether they're overlapping with the other one or they don't. There's another interesting feature, as probably, I'm so sure all of you know, the form of the density of states at the band edge is also universal within Bloch's theory. And in particular, it depends very strongly on dimension. You know that in one dimension, bands have a one-hole singularity, divergence at the band edge. In 2 dimensions, there is a jump. And in 3 dimensions, there is a square root singularity. This is true for any lattice in a given dimension, except for some very strange lattices. But generic lattices, whenever the band has a normal minimum and a maximum in momentum space, then the form of the density of states or the Green's function at the band edge is universal and depends only on the space dimension. What is remarkable is that within this CPA theory with disorder, the behavior is completely different. So in particular, the form of the band edge, both at weak disorder and strong disorder, is not dependent on the form of the bare density of states of the clean lattice, but it assumes a square singularity independent of whether you are in 1, 2, or 3 dimensions within this theory. So as you turn on the disorder, this strong dimensionality dependence of the band edge is gone. And you can show analytically using the same Landau argument that I've shown you, numerically and analytically, that CPA gives you a universal band edge of the squared shape. So that's one interesting feature. The second interesting feature is that as we start closing the gap at weaker disorder and the two bands start overlapping, because the disorder is now mixing the bands, there's scattering between the two bands due to disorder, the two bands are not, the band index is no longer a good quantum number. And you no longer have two bands, you only have one band. And the density of states, the Green's function, the spectrum is smooth and analytic within this entire band. There are only now 2 branch points, not 4 branch points. Notice that when the two bands overlap in the block case, we have a non-analyticity here when they are just touching. So you have a cusp. Here there is no cusp. In fact, here also you have one-hole singularities, no one-hole singularities here. So it's remarkable that the CPA has these sharp band edges, but the number of these branch points changes, and the changes in a singular way at the transition, which is now seen as a real phase transition. So the point is that phase transitions in general are points where all physical quantities change in a sudden and non-analytic way. You can see that in the block case of band overlap, this is not true. Everything is evolving smoothly. Each band is evolving smoothly. Here, we have a singularity at the critical point, and the two branch points merge together and annihilate each other, and then the number of branch points changes from 4 to 2. This is something that all of this you can show this analytically using this Landau approach.
Vlad,
yes.
Here a question Hannah
yes.
asked about what is X?
Oh, X. Oh, I'm sorry. This X, for some stupid reason, that was the site energy. My student sorry for that. This was just she used that for site energy. I don't remember why. It doesn't matter. The point is that here you have a binary disorder with 2 site energies, and you're just increasing the splitting. Right? That's what gives you. But this is just a simple binary disorder, exactly of the same type that Hannah has studied with much more powerful methods with using cluster expansions. Here, this is a simple single-site CPA result. But again, what is kind of remarkable, I find 2 things remarkable. One is that the form of the band edge singularity here in CPA is completely different than in the block theory. The second one is that there's a qualitative difference between the insulator and the metal, and there's a sharp transition where these 2 band edges annihilate. So this is a real critical point, and it has analytically the same analytical structure as phase transitions in the standard Landau theory. So I found this very surprising and very exciting, because it suggests that, in fact, there is more similarity between this type of transition and the usual phase transitions. Now, I would like to show you this result from another perspective. And this perspective goes back to the history of phase transitions, where we learned from many studies of critical phenomena that phenomena like ferromagnetism, antiferromagnetism, whenever we have a spontaneous symmetry breaking, that phenomenon can exist only in the thermodynamic limit. In my lecture notes in the course that I developed previously at FSU, I show a particularly nice homework assignment going back, which I found in the Kadenov's book, which shows that for an infinite range model, you can exactly solve the problem using saddle point expansion, but not only in the thermodynamic limit, you can solve it for a finite system. So you have 2 limits that you can examine. One is the limit of infinite number of sides, the thermodynamic limit, and the other one is the limit where you turn on the magnetic field to break the symmetry, and then you turn it off. We find spontaneous symmetry breaking when we apply a symmetry breaking field and then turn it off, and the other parameter remains finite. But these two limits, as you can show in this simple example, they do not commute. So the sharp phase transition is not found for any finite system, and the reason is the following: that for a finite system, all the spins want to line up, but there's a finite probability that all of them will eventually flip down. In the language of Landau theory, the free energy has two minima, and these two minima are separated by a barrier. The size of this barrier grows to infinity exponentially in the thermodynamic limit. But for a finite system, the barrier between the two minima is finite, and thermal fluctuations can take you over. So the system will never really freeze. So people say that spontaneous symmetry breaking is a form of ergodicity breaking, in the sense that in an infinite system, you find yourself confined to one of the values of the free energy, and you cannot explore the other value. Again, what is remarkable is that you show explicitly in these examples that I mentioned that any second order phase transition will be smeared for a finite system. And in fact, the smearing can be described by finite size scaling, which is used usually as a powerful tool to analyze numerical data on critical phenomena. So people usually analyze Monte Carlo data using finite size scaling, and it's all based on this understanding that real sharp phase transition only exists in the thermodynamic limit. This has also been proven more rigorously by Li and Yang in their famous work in the 1950s, which analyzed, if I remember, the partition function of an Ising model. They analyze it for finite systems and for an infinite system in the complex plane, where you extend the temperature into the complex plane. And they showed that turns out there are poles of the partition function on a circle, which pinches the real axis only in the thermodynamic limit. So they've proven in this famous work, and part of their Nobel Prizes for that, that the sharp symmetry breaking second order phase transition can exist only in the thermodynamic limit, but not for finite systems. And this is one of the most characteristic and robust features of all known critical phenomena. Now I want to show you that, in fact, this exactly is true even for CPA. But before I do this, let me just say that in CPA, as it turns out, or in fact in any DMFT-like theory, the only information about the lattice, or the geometry of the lattice, is contained in the form of the bare density of states. In this case, the clean density of states can have any specific form, and you can use this as an input in the CPA equation. So all you know about the lattice is the density of states. Now, I should emphasize that the density of states is not a unique feature of a lattice. There are typically many lattices that may have the same density of states. And those of us who are DMFT people, they know that, for example, the semicircular density of states, which has been used in the history of solid state physics many times as just the simplest model of a band, or featureless model of a band, in fact becomes exact in two different lattices in the limit of large coordination. One is the beta lattice, which gives you semicircular density of states in the limit of many neighbors. And that's why people always say beta lattice, and then the referee say, but this is unphysical, blah, blah. But there's another lattice, which is the lattice where you take n sites, and each site is connected to every other site by hopping element Tij. You take Tij elements to be randomly and Gaussian distributed, and in the thermodynamic limit, you can easily show that this random matrix also gives you the semicircular density of states. So these two lattices give you an identical CPA equation if you add this order. And so again, we can choose, if we want to understand the CPA equation, we can choose any lattice we want. And it's particularly nice to do numerical work to use this infinite range model with random Tijs as an interesting representation or realization of this particular semicircular band. And this is what I do here. So I take a model where I have on the diagonal, this is a Hamiltonian matrix for the tight binding model. I have two site energies, minus x and plus x. So x, big X stands for site energy. So half of the sites have minus x, half of the sites have plus x. So this is typical binary disorder. And the rest of the Hamiltonian is full with elements Tij. Every matrix element is Tij. So these are random, and they are Gaussian distributed. So this is a simple random matrix of the type that Wigner and Dyson have studied, except that on the diagonal we have two different values for the site energy. So if they're all the same, then we would just get a simple semicircle, as everyone knows, going back to Wigner and Dyson. But if we actually put this binary disorder here, then we can see how the band splits and how CPA describes a disorder-driven metal-insulator transition. And what's particularly nice for this representation is that you can do it for a finite number of sites. And in these plots, my student Yuting took this matrix with 200 sites, generated random hopping elements Tij from a Gaussian distribution, and then obtain these energy levels. So for each value of disorder, you can simply diagonalize this matrix and you find 200 eigenvalues. As you vary the disorder strength, you can follow these energy levels. And you can see here when T over X is very large, so a disorder is weaker, we have a single band. And you can see these energy levels are not periodically distributed, they are a little bit random because this is just a random matrix, obeying Wigner-Dyson statistics. But at some point, this blend splits into two bands. And in the thermodynamic limit, there's a sharp transition here. Now, we would like to zoom in at this transition and see what happens to these energy levels. And what you can see is that for a finite system, any finite system, these levels evolve from this side to that side continuously. So here is a blown up picture of that. See, this is energy range from minus 0.1 to 0.1, so this small energy range. And you can see here individual levels, which see how randomly they wiggle because this is a random system, but they never cross. They never cross, and this is a famous phenomenon of level repulsion that Landau, I don't know who was the first person in quantum mechanics to learn, that if you have two energy levels, but if they're hybridized by any hybridization, any matrix elements connects to quantum states, then you will find the phenomenon of level repulsion. So some people call it avoided level crossing. So for these kind of random matrices, you have energy levels, but they never cross. And so you can see that here we have a whole bunch of levels. They never cross. The yellow levels are negative, the blue levels are positive. And notice that these curves are not particle Hall symmetric simply because a finite system with random site energies is not particle Hall symmetric for a given realization, even though the average density of states will become particle Hall symmetric after you perform averaging of a disorder for a finite system, or if you go to the thermodynamic limit. So you can see the levels are repelling each other, obeying Wigner-Dyson statistics, but at some point, these two levels, which are the closest to the Fermi energy, look at what happens to them. On the right, they are very close to each other, and this level spacing will become even smaller and smaller in the thermodynamic limit. Eventually, you will get a continuous spectra, but on the left, they split out. But you also see that this splitting between the two closest levels, the occupied levels are yellow, the empty levels are blue. The gap at the Fermi energy is always finite for a finite system, and so there is no phase transition for this finite system. The level spacing goes from large to small between these two levels in the middle, but there is no sharp feature here. The sharp feature is obtained in the thermodynamic limit, which you can eyeball here, when the level spacing on the right goes to 0, but on the left it remains fine. So this is another beautiful example of how this transition, which looks very much like spontaneous symmetry breaking transition in the IZ model, is actually seen also in the phenomenon of finite size scale. So this is a true critical phenomenon, almost identical to that found in the IZ model. Now let me show you in contrast what happens if you have two bands, if you have a block case. So now we can also use a random matrix representation. But the only difference is now that the matrix elements are differently distributed. So this is a model with it's a model with two sides per unit cell, where there's a dimer in each unit cell, with element T perps and T, which are different. The T perp is the hopping element within the dimer, and the other ones are connecting dimers. So this is a model that gives you two bands, which are periodic, and then you have a simple phenomenal level crossing. Now we can also diagonalize this Hamiltonian and follow the energy levels. And what you find is this. You see, we have, again, discrete energy levels, but these energy levels spread out, and they do not change when the two bands overlap. You see, they smoothly evolve, and they cross. You use the blown up picture. You can see that the blue and the yellow levels, they simply cross. Why? Because if you diagonalize this matrix, if you go to the bonding anti-bonding representation, you will find that the Hamiltonian becomes block diagonal, and these yellow and the blue levels, they have a different band index, and they don't talk to each other at all. They're completely independent. If you introduced some additional disorder in this model, which would mix these bands, then immediately this would change, and these levels would display avoided level crossing, level repulsion, and will go back to the previous universality class. So you can see that this is completely different than this. Here we have a level repulsion, Wigner-Dyson statistics, and we have a phase transition in the thermodynamic limit. Here, for finite system and for an infinite system, we have the same behavior. We have level crossing, and we have no phase transition. So this shows you, I think, in a very vivid way, how different this CPA transition is from the band crossing transition. At first sight, we'll just have overlap or we don't. But if you look in close detail at how this happens at the analytical structure of the electronic states, at the point where the bands split, you'll see that they are completely different in the two cases. And the CPA case is remarkably universal and displays all possible features of quantum criticality, including scaling. But I think that this has not been appreciated, and we are planning to write a paper on this, showing some of these results with random matrices, because lots of people have studied random matrices, and this is very clearly seen. This particular feature is very clearly seen in this representation. I would like also to mention that this type of model can be, in fact, analyzed further away from mean field theory. It is possible to derive the CPA type of equations as a settle point in a functional integral and do systematic loop expansion around this mean field theory in the exact same fashion that Wilson did for the Landau theory. So this kind of Landau theory that I'm describing here can be systematically improved in a Wilsonian way, and this opens a direction to study this type of phase transition systematically beyond mean field theory in a way that is parallels and mirrors exactly the history of critical phenomena. So now let me show you at the end some results, and I will not go into any details. These are results on the Moiré material where we have a narrow band. If you are sitting at the middle of this band, you can tune the bandwidth to study the Mott transition. And in fact, in a Nature paper by the Cornell group, they've studied this Mott transition, and it displays all possible features of standard Mott transitions found, for example, in motor gains. However, if you completely fill the band, and there's a gap to other bands, and then broaden these bands to close the gap, so you have basically a band transition, then you find this family of curves where you can see the residual resistivity is smoothly going up, and its inverse, the conductivity, is coming to zero linearly, smoothly at this particular point. Oops, this E is the electric field they use to tune the bandwidth. On the insulating side, you have activation, you have an insulator, and the activation gap vanishes at the same point. They find some linear resistivity at low temperature, which is confined below some temperature T star. That temperature T star also vanishes here, and the slope displays this behavior, the slope of the linear resistivity goes first up, crosses zero at some point, and then goes down. This is very natural and is seen in all possible disorder-driven transitions, that the resistivity is initially low and you see metallic behavior, but as the residual resistivity goes up, eventually the slope of the temperature-dependent part changes sign, but it happens typically before the transition itself. And we can see that it happens here. This black dashed line indicates where the slope changes sign, and the transition itself is a little bit further down the road. So there is a very good evidence that everything displays power law behavior, and you can in fact take this family of curves and scale them in the following way. You can find where the transition is. If you look at the temperature dependence, you find that it has a power law form, 1 over T. This is experimental data. This is one of those curves. And then you can divide resistivity by this critical resistivity, rescale temperature by the some temperature T0. That temperature T0 is a power law function of the distance to the transition shown here. And then you can scale the data in this beautiful scaling plot, whereas the red line is from our theory that you think developed, and the dots are the experiments. You see, the scaling works perfectly well. This is one of the best examples of scaling I have ever seen. And so all of these features indicate a second order phase transition. Here, the theory results that you didn't obtain and her phase diagram. So you can see we have a very, very simple theory. It displays all possible features of quantum criticality that you may wish. It is extremely simple. We understand it very well semi-analytically, but it agrees with this experiment remarkably well also. So again, I want to emphasize that this is a huge discovery to me, because for many years I believed that CPA sucks. Now, it seemed to suggest that given the fact that interactions can make disorder in many cases to be bimodal, then CPA may be essentially all you need to describe many disorder systems. Of course, there are phenomena beyond that. Of course, this is mean field theory. This is an approximation. Perhaps if we could approach the transition very closely, be super close to the transition, we will find that we expect this theory to break down, just like any mean field theory should break down. But we also have a path to develop this theory further and to go beyond mean field theory. So now let me conclude. So what I try to tell you today is that CPA-DMFT does not capture unanswerable causation at all. But remarkably, when the disorder is bimodal, it displays a second order phase transition, which is a disorder-driven transition, and that transition survives even to infinite dimensions. So it seems that this disorder-driven transition where the band splits, it's a mechanism for a disorder-driven transition which is much more robust than even unanswerable causation. It's something that seems to display all features of quantum criticality, but it's also something that is very generic, because it seems that we have arguments and some examples so far where we claim that interactions make this phenomenon occur pretty much in any real system. What's also remarkable is that this theory is so simple that some features of the transition, like the critical exponents, we can compute them exactly using the same idea as Landau theory, and this opens a direction for future work. So in particular, we've studied only one simple model of interactions, which is the interaction of the electron with a certain bosonic mode and disorder. And this displays certain generalized polaronic effects, but probably similar phenomena are found in the case of magnetic polaron, Coulomb glasses, and many other systems where there's a non-local interaction where the site interacts with an environment, and this environment can respond differently depending on the site occupation in the limit of strong disorder. So this kind of polaronic effect seems to be a magical wand which will completely modify the transition away from the Anderson picture. What's also remarkable about this theory is that it assumes a very simple Landau structure, such that it's possible to perform systematic corrections to this theory. We can do loop expansion. We may be able to develop a randomization group formulation, but we also can do cluster approaches in real space to study this type of transition in even greater detail. So I think this seems to offer a pretty cheery look for the future of modeling disorder and interactions. And in particular, I think for this collaboration, where we're trying very hard to see how much mileage can we get out of the even simplest approximations like CPA when coupled to a realistic description of electronic systems based on DFT and its extensions. So it seems that this result suggests that, in fact, that program is perhaps much more promising than I even expected. So with this, I will stop, and thank you very much for your attention. And I'm happy to answer any questions anyone may have.
Thank you, Vlad. It's a very nice talk. That's great. Let me turn off the recording so we can start to have a discussion.